So we started to talk about the figure and axis object and how to work with them. And we saw one way, which is actually two ways. We saw we could create figure and then adding axis to it, or we can create them together right away using the subplots function. Another way to create and work with axis is the following. You can create a figure like before. And then within the figure object, you can use the bound GCA function, which is short for get current axis. And that will give you the last axis that was created using this figure. And if no axis was created, like in this example, it will create a default axis that encapsulates the entire figure and give you access to it. And then you get a reference to the axis. And you can see that we get an axis, and its type is actually an axis subplots, like when we use the subplots function. And we can use it to plot different things. Can you please close the door? Thanks. OK, notice that if a figure has several axes, like in this example, we create subplots with 2 rows and 2 columns, and we use the GCA function, then we'll just get an access to the last created axis, which is, in this example, the last one. So the last row and the last column. Only if it's very obvious which was the last axis that you actually used and you want to use it. I actually don't like it that much. I typically don't use the GCA option. I think it's too ambiguous and not a careful way to work with matplotlib. There are actually many ways I dislike about matplotlib, being too ambiguous and giving you too many ways to do different things. Some of them are really not optimal. That's one example. So I actually encourage you to mostly use just a subplots function. By the way, if you don't give it any parameters, if you don't specify the number of rows and columns, then by default it's just 1. And it will give you a figure and an axis together. So you just get a figure, you get an axis, and you can start working with it. That's like, I think, like 99% of the cases will do what you want. So that's, I think, the simplest way to work. And yeah, like we saw, we can use the same axis to plot different plots. So here we have 2 lines, a red line, and an orange line, all within the same axis. And what I want to show here. Yeah, OK. So we also have a shortcut. Again, it's another kind of shortcut interface that Matplotlib gives. So instead of using functions for figures over the axis object, you can use it for the module itself. It has a plot function which corresponds to plot of the GCA, of the last used figure. Again, a shortcut. Again, somewhat ambiguous. Again, not recommended. And I will show you in more details why it's not recommended to use it. It's even inconsistent in many ways with the standard API. So I strongly recommend you to just work with explicit figures and explicit axis objects and do everything with them. OK, let's talk about artist objects. So actually, every time that we create this plot or chart or something within axis, we get what is called an artist object. For example, when we use the plot function, we get something in return. And if we look at what we get, we see that it's actually a list with just one element, like you see here. So we can use the glorious comma notation to get it out, this one element within this list, and get the object. And you can see that it's aligned to the object, this added line that we created. And that actually represents this line that we created using the plot function. Now we can use the Python isInstance function, which tells us whether a certain object is of a certain type. And we can see that the added line is, in fact, aligned to the object, but it's also an artist object. That stems from something which is called inheritance, which we haven't yet spoken about. We will speak about it later in the course. But what we need to understand is that types in Python are hierarchical. So we have the line to the type is a subtype of a more general type, which is called the artist type, which allows us to do all kinds of things. For example, many artists objects have a set color function, which allows us to change the color in retrospect of some artist object that we created. So if we create the line using a plot function, if you remember, by default, it will create a blue line. But then we can use the set color function to change its color. And again, that's not a recommended way to do things. If you want to create a red line, it's better just to say that you want it to be red just at the beginning using the color attribute argument of the plot function. There are reasons to do all kinds of manipulations on the artist object, as we're going to see, but that's not one of these use cases, actually. OK, let's speak a little bit about annotations and things we can use to augment our figures. So in this example, again, we create all those lines within this axis, and we then collect all the artist objects that we created into a list with now two artist objects, which is called lines, which will have the green and the blue curve. Now let's see different functions we can use to add some annotations and texts on this figure. So the axis object as a set title function, which will create a title to this axis, and we have the set x label. We set the label for the x-axis, or likewise the y label. Set y label. We set the text annotation for the y-axis. And we also have the legend function, which will create this nice looking legend at the corner of the figure. And the way this works, we give it a reference to the artist object that we want to create legend for. So if we remember, we created one green line and one blue line, and the lines is just a reference to these two objects. And when we give it to the legend, it knows how to create this nice, short, compact representation of them, which correspond to the actual line that you see in the figure. So you see this big blue line. It represents as this short curve. And next to it, it puts the text that you wanted to hear. So the first one will get the label, that label, and the second one will get that label. And this way, you can create this nice legend. Yeah?
Can I change the location of the legend?
Yes, you can. I think I have an example of that. Yeah, OK, great question. So here we have some customization that I wanted to show you. So first, as to your question, yes, we can change the location of the legend using the lock argument, which can just get this text, which says where you want it. So if you want it on the lower left corner, you write lower left, and it knows to put it on the lower left corner. And another customization that you see in this example is setting, changing the font size of different elements. So we can set the font size for the title, for the X label, for the Y label, everything we want. We can make this horrible looking gigantic fonts that you see here. And if you want to read more about different options that you have for legends, you can visit this URL, and you can see many more options that you can use. Now, we've seen that the axes have, each of them they have the set title option, which create a title for the axis object, like you see here. So here you can see we create a green title for each of the individual axes. But then we may want to create some super title for the entire figure. And we can use it using the subtitle function of the figure, not the axis. And you see now it creates this super title on top of everything that is for the figure, not for the axis. And yeah. Another thing we can modify is which part of the plot we want to zoom into. So we have the set xlim and set ylim functions, So if we create a figure, by default, it will show everything. So it will take it all the way from the minimum x value to the maximum x value, and from the minimum y value to the maximum y value. But sometimes you want to zoom in or to zoom out to more concrete type, and you can specify some concrete range. So we want the x-axis to be between -2 to 8, like you see here. And we want the y-axis to be between 0.5 to 1.5, and that's exactly what we get, like we wanted. Now we can also set what is called the ticks. Those are the annotations on top of the axis specifying the numeric values. So for example, we may want more ticks on the x-axis, and we can use it using the x-ticks, and we actually specify the concrete values that we want. So here we use the arange function all the way from the minimum to the maximum, but with jumps of 0.4, and that's exactly what we get. Or we can create a very strange and uneven kind of ticks if we want, just by specifying concrete values, and we'll get that. Now, if we want to change some attributes like the font, we can use the tick params function. Again, I think not the most brilliant API, but that's how it works. So we need to use another function to change the attributes. That's the function, and we say that we want it just for the y-axis, and we want to change the label size. Now here we change the y-axis, but we could also specify the x-axis, or we could say both if we wanted both axes. Sometimes we also want to add a grid, like you see here. So it's easier to follow and see what are the exact values of each point in the graph. And we can simply do it by the grid function and giving it true. And again, notice that all of those functions are functions of the axis objects, not a figure. We can also create arrows and lines. So let's begin with lines. So if we want just an horizontal line, we can use the x-age line to create a horizontal line. We specify the y value that we want to create. So here we want a baseline of 0. And we can specify color and different other arguments. To create an arrow, we can use the annotate function. And this gets a bunch of parameters. So first, we give the text that we want this arrow to show. And then we give the x, y attributes, which is a tuple of x and y, as the name suggests, specifying the head of the arrow. So that's a point that you see over here, the place where you want to point to. OK, so we want the x-axis to be f of pi, and the y value we want to be 1. And then you have the xy text, which gives the x and y values of where you want the base of the arrow, this part. And we can specify font size of the text. And then we can give another dictionary which specify additional properties of the arrow. For example, we want the face color to be black. We want the width of the arrow to be just 1. But we want the head width of the head of the arrow to be 5. And all of those parameters, there are many more. You can look at the API and the documentation and see all the different things you can modify and change from the default behavior. Yeah, like if I, yeah, all of those parameters. Like if I didn't specify any arrow properties, I just finished it here, then I would have some parameters by default.
There's no arrow.
Yeah.
So if you want an arrow, you have to.
Yeah. Yeah. But by default, it will not show. Yeah. What else? OK, so let's go back to the line plots that we created. So if we use the plot function, we can change the width of the line using the line width function. And we can also change the style of the line with the line style function. And you can see all the different options here. So by default, it will be just one solid line, but we can have it a dashed line, or a dotted line, or a combination of dashes and dots, like here, using the dash dot option. And for each of those, you can either specify through English text, or you can provide those shortcuts of those symbols. So twice the dash symbol will be a dashed, a colon will specify a dotted, and a dash and the point will be a dash dot will be this dash dot option. Okay. So we covered all of the basic of matplotlib and how to define figures and axes and how to specify all kinds of modifications. Now let's start going through the different kinds of plots that we spoke about at the beginning of the class today. And let's actually begin with the CDF, the cumulative distribution function, because that actually, if you think about it, is nothing more than a line plot, just with very specific values. So here we create, let's begin with creating the data. So we create some data with 10,000 data points. It doesn't matter what exactly, we get some distribution of data points, and you can see, for example, the first 10. Now, to create a CDF from that, we want to create, again, a function that starts with 0 for the lowest value of x and ends with 1 for the highest value of x. And then for each x in between them, we want the value to be the percentage of points which are lower or equal to that value. OK, so for example, you see we create a for loop trying different thresholds, and we see that for each of those we take the data and we compare it to the threshold, and we then take the mean. OK, let's first maybe understand this code and what it does. So when we compare the data to a threshold, we get a Boolean mask. OK, that's a NumPy. That has nothing to do with matplotlib, what we do here. We compare the NumPy array element-wise to a given threshold. And we get a Boolean array that for each element says whether this element is lower or equals to the threshold. And if it is, we get true. Otherwise, we get false. So that's a Boolean array. Now, what happens when we take the mean of a Boolean array is that by default, all the trues are treated as 1, and the false are treated as 0. And so we get the number of 1s divided by the overall number of the overall size of the array. In other words, we get the proportion or the frequency of trues or masks. So that will give us the percentage of values that meet this criterion that we specify here. So it will essentially give us the percentage of data points that are below this threshold. And then we can print it and get that. We see that 25% of the data is below 0, and 50% is below 5, and 75% is below 20. And that's indeed what we see in the CDF that we created. You see that for 0, we get roughly 25. For 5, we get 50. And for 20, we get 0.75. OK, now let's understand how we draw this line using the plot function. OK, so to do that, we use the plot function. And now what we give it for the x values is a sorting of the data. And for the y values, we just give a spacing between 0 and 1 with jumps with a number of data points. So essentially, it will be 0, and then 1 divided by the number of data points, and then 2 divided by the number of data points, and then 3, all the way to 1. Now, the reason it works, and it does produce the kind of CDF that we want to create, is because we sort the data. So we sort it. We take the data, and the x begin with the lowest and ends with the highest. So the lowest value will get a 0, which is the beginning of this space. And then the second one, the second lowest value, will get 1 divided by the number of data points, which is exactly the proportion of the data points which are below this value. And then the third one will get 2 divided by this number. And this way we get indeed what we want, everything between 0 to the number of points. And that's exactly the CDF. We then connect it with lines, and we get a CDF function. Is it clear? OK. So to create a CDF, we can just use the plot function. Now, how to create a scatter plot? So let's begin with the examples. We will start with loading our favorite data sets, ViperDB, into a data frame. And let's try to plot all kinds of figures with this data. To create a scatter plot, we just use a scatter function of the x-axis object. So again, we just specify the x values and the corresponding y values, which in this case are just different columns of the same data frame. So we want the inner radius to be the x-axis, and we want the outer radius to be the y-axis. We want the color to be black, and we want it with no face color. So by default, it will be solid circles filled with black also in the middle, but we want it to be white so we can actually see the density of the different records. So indeed what we get is we get this nice scatter plot where each point represents a virus record within the ViperDB database, and the x-axis is the inner radius and the y-axis is the outer radius, like you see here. Okay, now let's create this figure with a little bit more customized look to it. First, we want to get rid of this outlier. You see, it's not a terrible outlier, but it somehow distorts the plotting. So just because of this guy, we need to use a different resolution for the figure. So to get rid of it, we just filter the records, which are below 500, according to the y-axis, which is basically everything other than this record. And once we get the filtered data frame, again, we use the scatter to take one column as the x-axis and another as the y-axis. And now we actually take the color to be red. And as standing for the size, we want a different size, so we use 80 to make it slightly larger. And there is this alpha argument, which specifies how transparent we want the points to be. So if we use 1, that's the default. Everything will just be fully opaque. And if we give 0, then we actually see nothing. It's fully transparent. So 0.2 is like 20% through, so it's 80% transparent. So we want it to be mostly transparent. And the reason that we do that, again, we want to see density. So now that everything is somewhat transparent, we can see that here we actually have many records. And we see that now that they're on top of each other, and they make the color much more vivid than in places where we just have one record, and it's quite transparent. So it's a nice way to actually see the density where we have this overlapping of records. And we set the x and y labels to specify what each axis stands for. So this is the inner radius in angstrom units, and this is the y-axis in angstrom units. And then we get this nice looking graph. Questions?
Why the U in the title? Label, you added a U before.
Yeah. Actually, I think it's not necessary. I think that, yeah. That's a leftover from the time where this notebook was in Python 2. So in Python 2, there was a problem specifying characters which are not exactly ASCII characters, like this funny A that you see here with this circle at the top. So that's a special character. And in Python 2, you needed to specify that you wanted to be a Unicode string to specify such strings with non-English letters. So for example, if you wanted to be in Hebrew or in Greek or any other language, you would have to say that it's a Unicode string. In Python 3, it's actually much better. And now everything is just Unicode by default. And there is no longer this problem. So yeah, it's not necessary. OK, let's make an even more fancy looking graph. The one you see here. OK, so what we want to see here, we want to show, again, the different virus records. And again, we show the inner and outer radius. But now first we want the size to reflect, what was it? I think the number of subunits is the size of each record. So you see some are large and some are small according to the number of subunits that viruses have. And we also colored them by the groups. So we took the 5 primary groups, like you see here. And each of them we gave a different color. And then we get this nice looking figure. So let's see the code that actually produces this nice figure. So again, we filter everything that is on the side that we want. And we also want the genome to exist, because we want to know which group each record belongs to. And then to take the group of each virus, we use the apply function, which we learned last week, which we can then give some function, which given the raw genome, will split it by spaces and take the first word, which will be the group. And then we get a series of the groups of each virus. We then use the unique function to create, to get just the unique groups, and we sort it alphabetically to get the unique groups, the 5 unique groups that you see here. And now for each of those 5 groups, we want to specify a color that it will show. So we could do it manually, just choose a different color for each group, but I prefer to do it with an automatic code, which would work just as well for any number of groups. To do that, we actually use the CM submodule of the plot module, which has all kinds of color maps, as we're going to see later. One of them is called the jet color map, just some random color map that I chose. And a color map is essentially something that you give it a number and it gives you a color. So that way we enumerated through the unique groups. Each of them we have the index and the group name. And by giving some function of the index, we get some arbitrary color out of this color map. And then we create a dictionary using this dictionary comprehension syntax that for each group will map to the color that we create for it. Okay, so we get a dictionary with 5 entries. Each group is mapped to the appropriate color. And now we use the group that we extracted and this dictionary to obtain the color appropriate to each of one of the records using the map function. So map just works on a series, and you give it a dictionary, and it gives you a new series that maps the original values according to this dictionary. So it will use this dictionary to map each group to the corresponding color and give you a series of the original size of the data frame that we work with. So if we print it, you can see that the colors, okay, is nothing more than the color for each one of the viruses. Okay, so we did this pre-processing step, and now we can actually start to create a figure. So again, we use the scatter. And you see we give it one column is the x values, and another is the y values. And now for C, we stand for colors. We actually, instead of giving one color for everything, we give it a series to specify a different color for each one of the records. And we give the series that we created. And now for the S, for the size, again, instead of giving a constant value for everything, we give it a series with the corresponding value for each entry, which will be just 0.6 multiplied by the subunits. And then for alpha, we take 0.3, because we want it to be somewhat transparent, so we can see the density of viruses. We set the X and the Y labels. And finally, we want to create this legend. So if you remember, a legend requires us to have those artist objects so it can paint and draw how each one of those legends should look like. Now, in this case, we created it using a scatter plot, and we don't have just one artist for each group. We have many different artists for each one of the groups. So instead of using a pre-existing artist object, we can just create a new object using the patch object type. And you see that up here, I imported the matplotlib patches, and I call it mpatches, and this mpatches submodule has a patch object that is essentially something that you just give it a color and you give it a label, and then you create this nice patch, this nice solid rectangle that has a specific color and has a specific label. And now, instead of giving the legend 2 different arguments, instead of first giving it the artist objects and then the legends, I give it all together using the handles argument. So the handles will be a list where each of those is a patch that has the color and the label that's saying what should be the label of each color. And you can see that this is created from the group to color dictionary, which just gives me the color and the group name of each one. So the color is just the color, and the label is the name of the group. And I want it to be on the upper left corner. Okay, so there is a lot going on here, but it's actually comprised of quite simple building blocks that we just use together to create these nice-looking graphics. Any questions? So yeah, like I said at the beginning, the API of matplotlib can be a little bit confusing and complicated at times. But like you see, we can do pretty much everything we want. It just might take a while to understand how exactly to do that, and searching a little bit online to find the right way to do that and seeing some concrete examples. And then you can take it and modify and create the kind of plots that you want to create. Finally, I will show you that we can also use transformations for the axis, like we discussed at the beginning of the lesson. So now, for example, we want to plot the surface area and the outer radius in the same figure. But the problem is that the surface area is many orders of magnitude. So it goes all the way from around 30,000 to over 10 million. So to show it in just one figure, it's better to use a log scale, like you see here. So we took it and compressed it using the log 10 transformation, and now it just goes from 4.5 to 7, and we can actually see everything on the same figure. Now to do that, we don't actually have to do anything special with Matplotlib. We're just using simple NumPy manipulations. We just take the series with the outer SESA values, and we just apply the log10 function within the NumPy library. And that will work on it in a vector as well, giving us the log10 of each one of the values. And the y values remain intact. And the only thing that is important and actually crucial to do is when we give labels to the axis, it's very important to specify and let the readers of the figure know that we have applied a log transformation, and now those values are not the surface area, they are the log10 of the surface area. And that's it. OK, so that was about scatter plots. Now let's speak about bar charts. So as this example, we are going to create a bar chart that for each virus family will give the average of, what is it, I think, the outer radius. OK, so we want the average of the outer radius for each one of the families. Let's see how we create it. So first, we take the unique families, like you see here. And now we use a list comprehension. So for each one of the families, we iterate through it, and then we query only those families using this mask. And we query the outer radius of these records, and we calculate their mean. So we get the mean of the outer radius of all the different families as a list. And now to create a bar chart, we just use the bar function. And we need to give it the x positions and the y values. So the x positions, we don't need to do anything special. We just give some range. So basically just the number of families, all the way from 0 to number of families minus 1. That would be the x positions. And the y values, we take what we calculated earlier, so the average outer radius per family. And we specify the width of each bar, so we want it to be 0.85. So we want to keep some spacing between each two bars, and we can give a color. And now to give to provide those labels on the x-axis, we just use the set xticks and set xticks labels. So xticks, if you remember, is what I showed you earlier, that we can set any ticks to be used for the axis. And here we just use the x positions that we took earlier, so exactly where we created bars. So again, between 0 to number of families minus 1. And for the tick labels, we want actually the family names to be those labels. So we just give the families, which is this array here. And then each of those tick will have a label which corresponds to the family that you see for the bar. And we want the rotation to be vertical. So we want them to be vertically and not horizontally like by default, because then they would just overlap and we wouldn't see anything. OK? OK, and again, let's see a slightly more complicated and more fancy version of a bar plot. So here, again, you can see all the different families. And then you can see their average radius. Sorry, the average of different radiuses, but we wanted to show both the inner and the outer radius in different colors. So let's see how we do that. So again, we extract all different families, and now we need to calculate 4 different arrays. We calculate the average of the inner radius and the outer radius of each family, like using the exact same technique as before. But then we also want the standard deviation, because we also want those nice arrow bars that you see here on top of the bars. So we also want the standard deviation of the inner and outer radiuses. Again, same x positions. And now we begin with creating the inner radius bars using the bar function and giving the x positions. And first we create for the inner radius. So we give the y values to be the average inner radius per family. But then we also want the y arrow bars, so we give the y arrow argument, and then we want that to be the standard deviation of inner radius per family, which is, again, we calculated it before. We give the width, and we want some color. So we put it in teal color. And then likewise, we create the bar plot for the outer radius, like you see here, using the corresponding values. So different values, and we want everything offset by the width. So we don't want them to overlap with each other. So instead of giving the x positions, we give the x positions adding to it the width. So we want them exactly next to one another. So we want the orange to start exactly where the teal ends. So that's why we offset it by the width of the bars. And then for the ticks, we want it to be in between. So we want it to be in between the inner to the outer radius. So we take the x position, but shifting it just by half of the width. And then you can see that the tick is always exactly in between the 2 bars. And again, the x tick labels, we want the family names. And we want to give it a 45 degrees rotation. So before it was completely vertical, now it's sufficient for us to make it in 45 degrees. And we want it to be horizontal alignment to the right. So we want each word to end exactly where the tick starts, so we can see exactly which label corresponds to each one of those ticks. And that's basically it. We create a legend like we saw before. So we just take the first artist within each one of the bars that we created and give an appropriate label. And we set the x and y limits, and we get this nice looking graph.